Hello, my name is Nan Wang. Currently, I'm a postdoc research fellow in Cesaro State 61. In this video, I'm going to present our work, FlashSwift, a configurable and more efficient range proof with transparent setup. This work is conducted by me and Dongxi. First of all, let me give an outline of our contributions. In this paper, we developed a new logarithmic-sized zero-knowledge range proof called FlashSwift in the discrete logarithm setting without using a trusted setup. It can prove that a committed value lies in the range between 0 and 2 power n minus 1. We integrate the techniques of the two state-of-the-art D-log-based zero-knowledge range proofs, namely Flash proofs and Swift range. To the best of our knowledge, it is the first configurable range proof that is adaptable to various scenarios with different specifications. The configurability allows to trade off communication efficiency for computational efficiency. At the time of writing, it also creates two new records of the smallest range proofs, 289 bytes and 417 bytes for 8-bit and 16-bit ranges, among all the bit decomposition-based ones without requiring trusted setups, respectively. It is well known that zero-knowledge range proofs involve large amounts of communication and computational costs, significantly impacts the performance of associated applications. The performance of the incumbent bit decomposition-based zero-knowledge range proofs remains suboptimal, constraining the broader usability and adoption. Moreover, a new problem is generally neglected for those resource-constrained devices. In case of any changes in efficiency requirements, software upgrades of a different range proof can be both energy and time-consuming. So we wonder, curiously, is there a way to combine the strength of the state-of-the-art range proofs to produce a stronger and a configurable alternative without resorting to a trusted setup? Let us have a quick look at the features of Flash proofs and Swift range. Flash proofs and Swift range are two variants of the bit decomposition-based range proofs. Flash proofs is the three-round zero-knowledge range protocol. It has n power 2/3 sublinear efficiency in both communication and verification. It achieves comparable verification efficiency to that of the most efficient ZK-SNARK that relies on a trusted setup. Swift range is a logarithmic-sized proof with linear verifier efficiency. The salient feature is that it achieves twice the verifier efficiency of the state-of-the-art bullet proofs. Our range proof is constructed from public coin protocols. Let me firstly give a simple example on how to construct such a zero-knowledge proof. A zero-knowledge proof is an interactive protocol between a prover and a verifier. You can prove the knowledge of a secret without revealing it. A prover sends an initial commitment. Then the verifier replies with a random challenge. The prover must send back some values computed with this challenge. And finally, the verifier can use these values to conduct a verification. The popular Fiat-Shamir transformation can help transform the interactive protocol to a non-interactive one. Swift range is composed of a zero-knowledge range protocol, Pi SRG, and a series of compression protocols, Pi QC. The compression protocol can reduce the linear-sized range protocol to logarithmic size. Our high-level idea of integration is to try to replace Swift range protocol Pi SRG with Flash proofs range protocol Pi FRG. However, it is not trivial to combine them together because there is an inherent incompatibility barrier between the two proofs techniques. In the following, we'll give an overview of the techniques of Flash proofs and Swift range. Let me begin with an overview of Swift range compression technique. Given a witness vector Z and two generator vectors H and G, satisfying the relation H to the power of Z times G to the power of minus square Z, is equal to a group element U. The prover recursively reduces the dimension of generators H and G and the witness vector Z until the dimension is equal to 8. The right subgenerators are raised to the power of C-1 and C-2, respectively. In each recursion, U does not have any exponents. The recursions terminate until the proof size achieved minimum. Let me introduce FlashProof's bit decomposition technique. The high-level idea is that if we can show that a value can be represented as a binary form, then we can prove that the value is non-negative. Assume we have a target value small x. It can be represented as the sum of a series values wi. If we can prove that each wi is either 0 or the ith power of 2, then we can say that x is non-negative. The prover firstly arranges the values w in a L times k metric. So she creates a series values VL, where each VL has k number of w values, separated by k distinct random challenges EK created by the verifier. RL are random values created by the prover. The verifier can create a series values FL by subtracting VL from the powers of 2. Here are FlashProof's 3 verification equations. In the first equation, multiplying FL and VL can generate a series cross terms in the challenges EK. If the quadratic terms EK squares are all cancelled out, then the verifier can be convinced that W values are either 0 or some powers of 2. The second equation checks each SK hide the number of W values in the kth column. The third equation verifies that the target value X is the sum of all the SKs. So it means that X is the sum of all the W values in the matrix. The major technical challenge for integration is that only the first equation is compressible. The second and third equations are not compressible. Although there's a witness vector VL in the second equation, there is only one generator G. To make compression possible, there must be a set of distinct generators for all VL values. Clearly, the third equation is not compressible either. So if we only compress the witness vector VL in the first equation, this will lead to the invalidity of the other 2 equations. So we come up with a solution to address this technical challenge. We leverage the folklore observation that checking 2 equations G power alpha equals 1 and G power beta equals 1 amounts to checking an equation G power alpha times y plus beta equals 1 for an arbitrary y. We concatenate the first equation and the second one by separating them with a random value y. We then subtly convert the left-hand side of the concatenated equation to the compression-friendly form required by Swift range's compression protocol. Next, we try to address the integration issue of the third verification equation. We can combine the right-hand side of the second and third equations by replacing the term sk-1 with the product of x and the remaining terms from S0 to sk-2. Our range proof has a distinguishing feature, configurability from other proofs. With different parameter k, our proof achieves different performance. We have a 2-gear setting in terms of computational efficiency. For low gear 1, when k equals 2, our proof had the smallest size but lower computational efficiency. When k equals n power 1/3, our proof had the highest computational efficiency but larger proof size. This property allows our proof to flexibly adapt to changing requirements in performance, eliminating the need for different proof, especially for resource-constrained devices. rather than performing an upgrade of a new range-proof implementation. Only a simple parameter k is needed in case of efficiency requirement change. Finally, let us have a quick look at the efficiency comparison with the state-of-the-art range proofs in terms of proof size, prover time, and verifier time. We add a new medium gear setting that demonstrates intermediate performance between the low gear and high gear ones. And we build 4 reader charts for different ranges where the closer the vertices to the center, the higher efficiency. Holistically, we can clearly see that our proofs in the 3 settings are positioned at the innermost part of the reader charts compared to the others. And thanks for watching. Please refer to our paper for more details.